Good morning, everyone. I think we'll get started. It's my pleasure to introduce today's seminar speaker for the Photosynthetic Antenna Research Center, and our speaker is Professor Devens Gust. He is a foundation professor of chemistry and biochemistry from Arizona State University. As described, he has a very distinguished career in research and teaching. He received his BS degree from Stanford University and PhD from Princeton. Did a postdoc at Caltech and then joined the faculty at Arizona State University. There he's been assistant professor, associate, full professor, chair of the department, chemistry, biochemistry. He's been director of the Photosynthetic Research Center there, and also he is the director of their Energy Frontier Research Center, titled the Center for Bio-Inspired Solar Fuel Production. Recognize that. He's traveled extensely and received recognitions in his travels. He's been visiting professor at institutions in Paris, Belgium, Australia, and France. He's a fellow of the American Association for Advancement of Science and a fellow of the Institute of Physics in London. For his research, he's received numerous awards, including the Photochemistry Award from the Inter-American Photochemical Society and the AZTE Technology Venture Innovators of the Year Award. He's extremely widely published with over 250 articles in scientific journals, and his research and teaching interests evolve around various interests in organic chemistry, including artificial photosynthesis, solar energy conversion, organic photovoltaics, molecular computing, and just general photochemistry. His work is really, should be really well known to all of us here. Some of us will remember 30 years of work by Devens and his close collaborators, Tom and Anna Moore, which, it's not a pun, inspired a lot of the work on bio-inspired photosynthesis. They were the first ones to achieve a stable, which means like a nanosecond charge separation in a molecular array involving the site of singlet states. Prior to that, it was only able to achieve triplet states. Of course, you know, singlet states is where you're going to need high energy photons rather than wasting a lot of it going to the triplet states. So they achieved that, and they've been just kept going ever since on these really beautiful molecular arrays and analogs that actually can charge separation and split water and protons and do other very beautiful chemical things. So Devens, it's a real pleasure to have you here today, and I look forward to your time.
Thank you very much, Dewey, for that very kind introduction, and I'd like to thank the organizing committee for giving me the opportunity to visit PARC and Washington University and learn about the research that's going on here. I think I'll begin by telling you something about Uncle Charles. He's actually, he's not my uncle, he's my grandmother's uncle, so I guess he would be my great-great uncle. But my grandmother grew up in Jerome, Arizona, which is a little mining town, and her stepfather there was worked in the mines there. So they were not a well-off family. In fact, that whole town became a ghost town later, and now sort of come back as an artist colony. But her Uncle Charles actually was quite well off, and he was from St. Louis area. And he'd made a lot of money as a liquor wholesaler in the St. Louis area. And he had all this money, and so the supposition was that when he died, he would leave that money to his nieces and nephews, because he had no wife, he had no kids of his own. So my grandmother was, didn't wish him any ill will, but she was looking forward to that inheritance because he was a rich guy. But Uncle Charles had other ideas, and it turns out that instead Uncle Charles Redstock gave a lot of his money away. And he gave $1 million to WashU to build Redstock Hall, and I think that cost $250,000, and another $750,000 endowment to keep it going. And he gave some money to St. Louis University and other places, didn't leave anything to my grandmother, which really infuriated her. So looking back now, since it's been about 85 years since all that happened, at least 85 years, then see what's come out of it. Then Washington University has a nice building, and if they've invested the $750,000 well, it should be a lot of money by now. And as far as I'm concerned, instead of living in a villa in the south of France and driving around in a sports car every day looking for another 3-star restaurant, I'm trying to make my living converting water into fuel using sunlight. So that brings me to the title of today's talk, which is Bio-Inspired Solar Energy Conversion. I'm going to tell you about some of the work going on in our EFRC, Center for Bio-Inspired Solar Fuel Production. Before doing so, I'd like to say a little bit about why we're interested in this work. And it's a little bit of preaching to the choir, I think, but it's worth doing. Of course, the problems come because we use mostly fossil fuels for our energy. About 85% of our energy comes from there. And as I see it, there's 3 problems associated with that. First of all, fossil fuel deposits are generally not located in the same areas where the people live who use those fossil fuels. And that leads, as you know, to a lot of geopolitical problems, economic issues of various sorts. Secondly, whenever we use fossil fuels, we generate CO2. That contributes to climate change. And of course, we generate other kinds of pollution from fossil fuels, such as, let's say, water pollution. You can remember the oil spills in the Gulf of Mexico and the North Sea. Potential problems with extracting natural gas from rock, air pollution, and so forth. That picture on the right came from the San Francisco Chronicle. It's a power plant in India, currently operating power plant in India. And then finally, burning fossil fuels is really not sustainable. We're going to eventually run out. And that's not going to happen for a while. There's enough fossil fuels around for a few hundred years, and that says to a lot of people, well, we don't have to worry. But if you think about it, civilization's been around for thousands of years, and I at least hope it's going to continue for thousands more years. And it's simply not going to happen if we depend on fossil fuels. We have to find an alternative energy source. So what would that source look like? Well, ideally, it's going to be widely distributed around the Earth. It's going to be sustainable, renewable. It should be as environmentally benign as possible, although nothing on the scale of which we use energy is going to be entirely without environmental consequences. It has to be massive in scale. Humans use about 14 terawatts today, and that's going up. It should be inexpensive if possible. If we look around for the ideal source, then we really only find, in my view, one possibility. Here's a graph I got from France, and it shows a number of renewable energy sources. I mean, interesting thing here is if you look at the x-axis, it's a log scale. And what that shows us is there's a tremendous amount more solar energy available than any of these other possible sources. And in fact, I think most people would agree that solar is the only energy source that has the capacity to meet all of human energy usage. These other things can help, but they're not going to solve the problem. And that, at any time, we've got about 82,000 terawatts striking the Earth's surface. We use about 3 terawatts in this country, about 14 in the world, and that's expected to go up to around 28 by 2050. So it's plenty of energy there if we can find out how to use it. So how can we use it? Well, one thing we can do is generate solar electricity, and of course we can do that now with photovoltaics. The problem is it's still expensive. And here you see this graph's a few years old, but it makes the point still, which is that solar is a lot more expensive than other sources of energy, and that has to come down if it's going to be adopted in large amounts. On my house here, I have in Phoenix, I have about 6 kilowatts on the roof of this building, and for 9 months out of the year, I generate all of my electricity needs from solar, and I make more power than I use, and I sell it back to the power company. In the summer, that's not true. I have to pay a lot more for air conditioning, and then I use a lot more than I make. But still, overall, it works out well, and it will probably pay for itself what the money I put into it in about 8 years or so at current electricity prices. The only way that I could afford it, though, is because I got a very nice rebate from the power company for buying the system and also tax credits. Otherwise, it'd be too expensive to pay off in any reasonable time. We need cheaper solar electricity. We also, though, need solar fuels. We need both electricity and fuels, firstly because the sun's intermittent. It doesn't shine at night, it doesn't shine at other times, like today. And we need electricity, or we need energy all the time. And secondly, the sun's energy is diffuse, and you can't power a land vehicle like a car or a truck in any practical way using solar energy directly, because you need too much area. I get emails from people every once in a while, and they say, what would it be like to make a photosynthetic human? Could you do that through some kind of genetic engineering so you wouldn't have to eat? And I first of all wonder, why would somebody not want to eat? That's one of my greatest pleasures. But other than that, if you actually think about it, the human couldn't look like a normal human because you wouldn't have enough surface area to power the body. You'd have to be able to have some kind of huge photosynthetic wings that you could sit out in the sun all day to absorb enough light energy to power your body. We need something that's more dense than solar energy. And the answer to both those problems is fuel. And certainly one of the most dense forms of fuel is fossil fuel, gas. However, we don't know how to make it in any practical way. We don't have a good technology for solar fuel, so we don't go out and buy solar fuel. On the other hand, there's a good natural technology, and that's the one we all know about here, all you know about, and that's photosynthesis. And that's really the only proven large-scale way to make solar fuel, make fuel from sunlight. It's been around a few billion years, stores about energy at the rate of about 125 terawatts, which is 10 times what humans use. Every year, about 10 to the 14th kilograms of carbon are taken out of the atmosphere by photosynthesis and provides energy for all life and most of our energy. So photosynthesis proves that the job can be done. So if there are any doubters as we go along trying to figure out how to do this technologically, you can always look at photosynthesis and see it's possible. Now, of course, all these organisms didn't evolve to make fuel for us. They evolved for their own purposes. And one of the results of that is that photosynthesis is not tremendously efficient, maybe 1% or less in these kinds of plants. And so we need better efficiency. We don't want to compete with other things for land usage if possible. And so that brings us to a possible alternative, and that's artificial photosynthesis. And that's what we're interested in our Energy Frontier Research Center, and that is using the ideas, the physics and the chemistry that underlie photosynthesis to make a technology for artificial solar fuel production. This is not a very new idea. Here's a quote from Giacomo Ciamiciano, who's one of the first photochemists. They just had about 2 months ago in Bologna, they had the 100th anniversary of this article that he published in Science. He presented at the New York Academy of Sciences back in 1912. And if you read this little excerpt from the article, the whole thing is very interesting. You should look at it. But even this little excerpt shows that Ciamiciano had this vision of humans learning how photosynthesis works and then using artificial photosynthesis to remove the reliance that they had at that time on coal. Now it's on oil, natural gas, and coal. And instead have a clean source of energy. Ciamiciano expected us to get this done pretty quickly, and we haven't got it done yet, but there has been some progress made, and I'll be talking about some of that progress today. I'm going to be illustrating with results from our work, but there's lots of important work going on in this area around the world. So how does photosynthesis work? If that's going to be our model, we need to understand something about how it works. I'm not going to try to tell you how it works, but I would like to just remind you of some of the basic steps that occur in this photosynthetic membrane. First of all, we have antennas, which probably most of you in this room know something about. And they capture light across the solar spectrum and move the excitation energy around in that membrane. And they also have other important roles in regulation and in photoprotection. And I'll be saying something about that a little bit later toward the end of this talk. Then we have the reaction center, Reaction centers are responsible for using the light energy to do charge separation, convert the light energy into electrochemical energy. Then we have the dark reactions, the catalytic reactions, catalysts for water oxidation, catalysts for CO2 reduction and biofuel production in general. Could be carbohydrate or precursors to biodiesel or hydrogen. Some organisms both produce and live on hydrogen gas. So that's our model. I think it's a model for lots of things. I think biology is a good model for what we want to accomplish in nanotechnology. It's a bunch of nanoscale units. They're all working together, all control one another, work with each other to carry out some large-scale function. And I think that's what we'd like to realize in nanotechnology, and it's something that nature already does routinely in many, many different areas. We can learn from that. Okay, so how do we make an artificial photosynthetic system? Well, we're going to also need these same kind of components. We're going to need antennas, reaction centers, catalysts for water oxidation, catalysts for fuel production. I think we're going to need stability and photoprotection. These are going to become practical. And very importantly, we're going to need it to put all these things together in an integrated system. So, it's good to work just on parts of the system, but ultimately they have to be combined in some way to make a total system. That introduces a lot of new problems that you don't run into when you're doing, say, an isolated catalyst or something like that. So that's our goal, to make something like this. Let's talk about the reaction centers first. Here's just the bacterial reaction center. Mostly protein. There are in it, however, these organic cofactors that do the photochemistry. There's the chlorophylls, special pair of chlorophylls that use the excitation energy to move an electron from donor to receptor to donor to receptor to donor, all the way across the thickness of the membrane down to the phenol, thereby generating a long-lived energetic charge separation. So the simplest way to sort of model this then would be to just have a light-absorbing donor and then some kind of receptor. That's been done chemically for quite a long time. The first link systems that I know were made by Paul Loach and by Taguchi in Japan back in the late 70s. And they were basically porphyrin-phenone type systems. Here I show you a two-part system with a porphyrin and a fullerene, which is a more modern receptor, just as an example. We have these two porphyrins now, which are the light absorbers, the electron donor species. We have the fullerene down here, the electron acceptor. And the idea is we can excite the donor, get electron transfer to the receptor. And this has been designed to take some advantage of some of the properties of these particular pigments. I won't go into that in good detail today, but I'll just say that this system, if you study it using transient spectroscopic techniques, you see very rapid charge separation, about 1 picosecond, and from the porphyrin excited singlet state, about 15 picoseconds from the fullerene excited state. Quantum yield essentially unity. And then we have slow charge recombination back to the ground state, about 2.7 nanoseconds. So it's about 2,000 times slower than charge separation. And this is a very large difference in the charge separation to charge recombination ratio. And it's because of a number of reasons, but some of them are the small reorganization energy of the porphyrins and the fullerenes, which, if you look at Marcus theory, that says we should work toward this kind of effect, and also the very rigid structure, which prevents the molecule from getting into conformations that have rapid charge recombination. And we store quite a bit of energy in the charge separation. So for a lot of points of view, this is a pretty good model, but it has a problem, and that is even that 2.7 nanoseconds is really not as long as you'd like if you want to find a way to use the stored energy for something useful. You'd like to have longer to access that energy before you simply get charge recombination. So, in order how to do that, we go back to the reaction center. And you note that in the reaction center now, we don't get an electron transfer directly from this special pair down to this QB. And that's because it's really too far away. That electron transfer would be too slow to compete with other pathways that deactivate this excited state. So instead, we have the electron move from the donor to the receptor, and then that acts as the donor to the next receptor, and so forth. So the electron hops across the thickness of that membrane in a series of short range and therefore efficient and fast electron transfer steps And yet the result is you have a long distance charge separation here, weak electronic coupling between the donor and the receptor, and therefore slow charge recombination. And that's the way photosynthesis beats this recombination process. So we can make model systems that do that. First one that Dewey mentioned back in the early 80s, but here's a more modern one. And it has, now this one has three components. There's a porphyrin, which is the light absorbing species, the fullerene, electron acceptor, and then this carotenoid polyol over here, which again means we recognize, and that's like related to beta carotene, and that's going to be a secondary electron donor. The way the molecule works is that the light's absorbed by the porphyrin, you get the excited singlet state. That very rapidly transfers an electron to the fullerene, in this case of 3 picoseconds, generates an initial charge-separated species. That has a lot of energy stored in it, but it's rather short-lived. It lasts only about 3 nanoseconds. So we'd like a longer lifetime, and the way we achieve that is through the carotenoid, which does then a secondary electron transfer to P+. And that happens in only 67 picoseconds, so it competes well with charge recombination. And that gives you the final charge-separated state shown here. Positive charge on the carotene, negative charge on the fullerene, neutral porphyrin in the middle, and then the lifetime in this case is a few hundred nanoseconds at room temperature, a microsecond or so at low temperature, and we still store about 1 eV of the photon energy. We have a yield of the charge-separated state of 100%. So by using this sort of multi-step strategy, then we can have longer-lived charge separation. And we've made systems which have longer lifetimes than these, up to hundreds of microseconds. So that's just an introduction then to reaction centers that can be made. Antennas. Say a little bit about natural antennas. Here's one that you're all familiar with. Bacterial antenna system. In this case, 27 chlorophylls in this ring, and 9 carotenoid polyenes, all absorbing light, moving the excitation energy around, ultimately into the reaction center where it does the photosynthetic work. Now, we're not able to make artificial antennas of this complexity, but we can make simpler ones. Here's one we made with John Lindsay some years ago. And John's group produced this antenna, which is the blue part, the zinc porphyrin, and they absorb light and they move excitation around among themselves, time constant 50 picoseconds, and then in our labs, Paul Liddell attached in this red porphyrin, which is the energy sink, and in the fullerene, the electron acceptor, and the red porphyrin accepts the energy in 30 picoseconds, and then we get electron transfer in 25 picoseconds to the fullerene. We generate an initially charge-separated species, and then the whole migrates out to the antenna. That happens in 380 picoseconds to give us a long-lived charge-separated state that lives for about 250 nanoseconds, produced with a quantum yield of about 90%. So this antenna works pretty well, but it's still a porphyrin-type antenna, and it turns out that these porphyrins and chlorophylls in the natural case can't actually do the whole job very well. And the reason for that is based on this graph from Devens Gust. You see that the solid white line there, that's the absorption spectrum of chlorophyll A. Very strong out here in the red, strong in the blue, and there really is not too much sunlight. Right in the middle of the solar, on the visible part of the solar spectrum, really not very much absorption by chlorophyll A. So what the organisms do is they use other auxiliary chromophores, like they use chlorophyll B, they use carotenoids, they use cycloerythrin, cyclocyanin. All these things cover this region. They all absorb light, and they move the excitation out to the chlorophyll A, where it can be used in the reaction. So I'll show you just maybe a couple of examples of non-porphyrin type antennas we've looked at. Here's one that's based on this phenylmethyl anthracene, which has an absorption spectrum much like a carotenoid. And then they have 5 of those antennas on there. And the idea is that those will transfer excitation among themselves, and then on to that porphyrin, which can donate an electron to the fullerene. In fact, if we do transient absorption, we find out that that all works. Quantum yield of charge separation is 96%. I'm not going to go over all the rate constants, but we get essentially 100% energy transfer to the porphyrin, and then highly efficient electron transfer, depending upon whether we have the zinc core from the 3 base, and then combination of charge separated. Here's a more sophisticated antenna with basically 3 kinds of antennas. So we've got at the top, we did phenolphine lampricines. Those are blue absorbers. In the middle here, we have these boron Lodippy type dyes, and those are green absorbers. And of course, the porphyrins at the bottom, they absorb out here in the red region of the spectrum. And altogether, then, this molecule covers essentially the whole visible spectrum. And light absorbed by any of the pigments ends up down here in these porphyrins. Now, this is only an antenna. It doesn't have any electron receptor species. We need to make a reaction center by adding an electron receptor. And the students who made this were basically tired of synthesizing these big molecules by this point. So what we did is we attached the acceptor, which is this fluorine, by simply attaching 2 pyridines to the fluorine. And then we have self-assembly of these pyridines to the zinc in the porphyrin, which is that molecule on the right. And that's the reaction center antenna combination. And that species does electron transfer as well as energy transfer. And all that works extremely well. The lifetime of the excited state is not particularly long because it's only a 2-part diode type system instead of a more complicated one. But the antenna part and the electron transfer all works quite well. So that's one example, or a few examples of antennas. And lots of others. Okay, so we can make at least in some way, the antennas, we can make the reaction centers. How about solar fuel? And what we need to do then is we need to interface those reaction centers to catalysts. There has to be a catalyst for water oxidation because if you look around at what the possible source of electrons are for making fuel, you got to remember you have to have electrons as well as energy to make fuel. Well, you have to have a source, and we're going to do it on a huge scale where basically have to use water for the source. So we need a catalyst that will oxidize water. And we need some kind of a fuel production catalyst as well. And ideally, any of these catalysts are going to have high turnover. They're going to be low potential, that is, low activation energy for their job. And they ideally will use earth abundant material. We've not generated any such catalyst yet, but we have at least made a system that will do the job. And this is collaborative with Tom Maloof at Penn State. And this system actually uses sunlight to split water and make oxygen and hydrogen. And what it consists of is the water here. Immersed in that water is a photoanode, which is much like the one we use in Grassel cells. It's nanoparticulates containing dioxide on a conductive glass material, chlorinated tin oxide or indium tin oxide, and then adsorbed to the TiO2 nanoparticles, which is the ruthenium dye, much as in the Grassel cell. If the dye is excited, transfers an electron to the TiO2. The electron moves through that network of particles through the conducting electrode into this wire, and it goes over here to this platinum cathode and thereby reduces protons to hydrogen gas. So we get hydrogen gas off this side. That means the dye oxidized. The dye then will be reduced by this iridium oxide particle. Iridium oxide is a good water oxidation catalyst, the nanoparticle, and collects 4 holes, and then it can oxidize water to oxygen. So oxygen bubbles off this side of the cell. And in fact, this does work if you apply a bit of a bias in this small bias with a few holes to get it from width to the weight. If the cell is working, here's the voltage plot of the cell, and the water split. And it works for quite a while. Eventually, though, it's going to die off to the settled dye off to the side. But the single dye is over quite a lot of time during the function of the device. So it works, but it doesn't work very well. So that at least gives us hope we can make a device. What we'd like to do is make it better. One of the main problems with the device is shown by some work that Tom Maloof did spectroscopically. And what you see here is that once you've oxidized the ruthenium dye, you've got the oxidized dye down here, and what it needs to do is accept electrons from the iridium oxide. And it does that with a time constant of about 2 milliseconds. Unfortunately, though, it can also accept electrons back from the TiO2 conduction band or trap state just below the conduction band. And that happens a lot faster. That happens in only 0.35 milliseconds. So charge recombination here is significantly faster than the desired migration of the whole to the iridium oxide. So that's a big problem, and we need to get over that. So recently we've been looking again to photosynthesis to try to figure out how. And if you look at photosystem 2, and you look at the part of it that does the water oxidation, light collection, and so forth, you see this picture over here on the left. And you see that there are these two chlorophylls, or four chlorophylls actually. The light's absorbed here, and then it gets transferred to this phyton and then on ultimately to a quinone. That leaves these chlorophylls oxidized, and then you need to move the whole out to the oxygen evolving complex, which is the manganese calcium complex out here. And the way that nature does that is it uses this tyrosine histidine pair here. There's a hydrogen bond here between the tyrosine oxygen and the histidine nitrogen, and through a proton coupled electron transfer, the whole gets moved from here to that couple, to the tyrosine, and then on to the oxygen evolving complex. So recently, some of the students in our lab then, particularly Jackson Negiato and Terry's Antonio Poblan, made this model system on the right, and we have a high potential porphyrin there. It's a fluorinated porphyrin, so it's capable of water oxidation thermodynamically. It has this cyanoporphyrin up here, which is an electron acceptor, sort of the analog of the phyton. And then it has this phenol benzimidazole couple down here, which is our analog of the tyrosine histidine pair. And the idea is this can do a proton coupled electron transfer to the oxidized fluorinated porphyrin. And we've done then transient work to see if this works or not. And we find that it's a little bit complicated, but basically it does what's intended. You have the excited state of either porphyrin actually. You get electron transfer then to form the initial charge separated state between the porphyrins. And then the whole does migrate out here to the phenol benzimidazole couple. And then that species has quite a long lifetime, about 2.6 times 10 to the minus 5 seconds for charge recombination. So we have a long-lived charge separated state, almost 4 microseconds. And as a result of this final proton-coupled electron transfer step. So we've been able then to, in a way, sort of mimic what goes on in that photosystem 2 system. So of course here we have no catalyst for water oxidation. We're working on attaching that iridium oxide particle, but we've done a sort of an intermediate step, as I'll show you here with Tom Maloof. We've attached that same mediator there, that same phenol benzimidazole couple, to the iridium oxide particles, which are in turn linked through this saturated spacer to the iridium oxide. And then we've also attached the iridium to the TiO2 and the iridium oxide. Then we have also attached to the TiO2 this ruthenium dye. And if you eliminate the ruthenium dye, then what happens is it injects into TiO2, and then we get migration of the whole over to the iridium oxide, and we get again water oxidation. And in fact, this system, even though these two species aren't linked together yet, we still have substantially higher photocurrent for water oxidation than we do with the same system that doesn't have this mediator on it. So evidently, this mediator does play a role in this system in promoting more efficient electron transfer from iridium oxide to the ruthenium dye. It's still not highly efficient, but what we hope is that once we get the final system made with these two guys linked together, that we'll be able to have a much higher efficiency. So we're working toward improving the quantum yield and overall efficiency of this device. On the other hand, it's never going to solve the world's fuel problems. And the main reason for that is that the components, I mean the iridium, the platinum, the ruthenium, those are rare and expensive elements. And indeed, most of the catalysts you see out there today for these various processes use such elements. And as our collaborator Tom Maloof likes to say, iridium is not the least abundant element on Earth. It's only the least abundant stable element on Earth. So there's not much iridium around. And short of harvesting an asteroid or something like that, it's going to be tough to find enough iridium to do much good. So we have to find how to do the same things with catalysts that are cheaper, that use less abundant or more abundant elements. And photosynthesis, of course, can do it. There's a water oxidation complex. It uses manganese and calcium, very common elements here in the oxygen evolving complex. And maybe we can learn from this how to do water oxidation. And we have people in our research group, Peter Froni and Hao Yan and Jim Allen, some others working on developing analogs of this water oxidation complex. And I won't talk about that work today. That's going on. On the reduction side, again, you want to look for nature for proton reduction, which is our initial goal in our EFRC. Then you find the hydrogenases. Of course, they use just iron or iron and nickel to carry out the production of hydrogen gas. And they work very well. They work as well as platinum in many respects. We've actually taken that cell that I showed you earlier, or a close analog of it. And instead of using a platinum electrode for proton reduction, we've used a activated carbon with some of these hydrogenases attached, and they work just as well. They're just as fast as a catalyst. But they have problems such as oxygen sensitivity. Of course, they're relatively big. So various people for a long time have been working on making models of this that are functional. We have people using some different approaches in our EFRC. There's Ann Jones, for example, and Giovanna Irlanda. Both of them have made some functional complexes based on the natural hydrogenases. They're working on making them better. Again, I won't talk about that work today. What I want to do instead is talk about a couple other things. One of them is making the system more efficient. And we can work on making these catalysts more efficient with lower potential and so forth. But still, it's going to be very tough to use a single dye to efficiently convert light into solar fuel. If you want to use light over the whole useful spectrum out to maybe 1,000 nanometers or beyond, it's going to be tough to do that with a single dye and a single photon per electron. So what we're planning to do here is to use a tandem system. We'll have two artificial reaction centers, and the first one is going to absorb the bluer light, and that's going to do the water oxidation. And then the second system is going to absorb the redder light, and that'll do the proton reduction. So I'll show you what the cell might look like schematically here. So we have on the left, the cell for water oxidation, and then over here in the middle we have the cell for generating the extra potential for proton reduction, and then the catalyst over here that does the proton reduction. So in this kind of a system, you're going to need 2 photons per electron. But on the other hand, you get to use twice as much solar spectrum. So you have twice as many photons you're collecting. So that's kind of a wash. The way you win, though, is that you have now plenty of extra overpotential to drive these catalysts, because none of them are perfect catalysts. They're not going to be perfect catalysts. You have to have some sort of extra energy to drive them at a useful rate. If you want to do that and get higher efficiency, you pretty much have to use a tandem system. And that's been demonstrated with a semiconductor system by John Turner some time ago at Incorporation. So we're working on making one of these. We've made some prototypes, but nothing published on that as yet. What I want to do for the rest of the talk here is I want to talk about photoprotection, because I think we're going to need that. Certainly, if we use these sort of biological or organic type of components in a useful water splitting system, and probably maybe for any water splitting system. And plants are very good at this kind of thing. They prevent photo damage in a couple of ways. First of all, they protect themselves by regulating photosynthesis. Okay, so they don't produce more the reactive species faster than they can use them. I'll be talking about that. They also have things like carotenoids, which can prevent singlet oxygen damage if you do make singlet oxygen, or prevent formation of singlet oxygen from triplet states. And they're also good at repairing the photo damage once it occurs. So all of these things are used naturally. I think we're going to need similar kinds of things in artificial systems. They're going to be very practical. So I'd like to talk about one of those, and that's regulation. We've worked in a number of those areas, but I'll talk about this one. Now, sunlight, of course, is diffuse, and so we have antennas in photosynthesis so that they can collect all the light that they can get and maximize the rate at which the energy comes into the reaction center. And basically, the plants gorge themselves. They eat more sunlight than they need most of the time for whatever reason, whether it's because they're afraid of missing out when the sun's weak, or they want to prevent things down below them from getting light or whatever. They absorb it in general more light than they need. The problem is that when the light gets really bright, then they can't stop absorbing light. And so they're going to be bringing in these high energy photons faster than they can use the redox equivalents that they're making, and that's going to generate things like singlet oxygen and reactive radicals and things of that sort that will ultimately kill the organism. So one of the ways that the plants and other organisms prevent this is by regulation, and they actually down-regulate photosynthesis. So they reduce the quantum yield of photosynthesis when the light gets too bright. So they can shuttle off some energy, just dump it when the light's really bright, and then still have enough energy when the light's dim to keep living. So is it possible to do something like this in the lab? Well, if you look at how this non-photochemical quenching, as it's called, works, there's a couple of mechanisms. I'll show you just one. This is in cyanobacteria. Cyanobacteria have these phycobilizome antennas up here. You're familiar with those. And they have in the phycobilizomes absorb the light, and they move the excitation down here to the reaction center. And they have this is the water oxidation center, and they have these things called orange carotenoid proteins in them. And normally, the orange carotenoid protein is not surprisingly orange. And absorbed light, it doesn't really have any effect on the chlorophylls or anything else. Photosynthesis just goes on as normal. But when these things do absorb light, they isomerize or change, let's say, they change structure with a certain quantum yield to this red form. And the red form is capable of quenching chlorophyll singlet states in some way and just dumping the energy of the singlet state off the heat instead of moving that excitation energy to the reaction center. So you basically get rid of some of the photon energy in this form. Now, thermally, the red form will convert back to the orange form. The way the system works then is that when the organism is doing photosynthesis, the brighter the light, the more the orange carotenoid protein gets converted to the red form, the more the chlorophyll singlet states are quenched, and the less efficient photosynthesis gets. So really bright light, photosynthesis isn't too efficient. Light gets dim again, you go back to the orange form, then the efficiency comes back up. So it goes up and down with light intensity. So we thought, well, can you make something like this in the lab? And what we came up with is this system. And it has some parts you can recognize. It has in the center this porphyrin, primary electron donor. It has two antennas here with this phenylethylamethicine. And then there's the fullerene over here, which is the electron acceptor species. And in addition, there's another species held on here by this rigid hexaphenylbenzene piece. And that's this, what I call the control unit here. And that control unit is a photochrome. It's a molecule that can exist in two metastable states. And one of them is this spiro state shown up here. And then the other one, under the influence of blue light, this isomerizes to this form down here, which is the colored form. And that form thermally returns back to the blue form. And that's the part that's going to control the efficiency of the artificial reaction. The way this works then is that if the control unit is in this dihydroenzolazine spiral form, then light gets absorbed by the antennas, or it gets absorbed by the porphyrin, and then we have photoinduced electron transfer to the fullerene. That happens in 2.2 nanoseconds. You try to remember that number, it's useful. The efficiency is pretty good, 82%. The charge-separated state lives for about 14 nanoseconds. So it's a typical kind of artificial reaction in the system. Now, when the dihydroenzolazine then isomerizes to the betaine form, which is this colored form, then we've set that up so that this form now is a very highly efficient quencher of the porphyrin singlet states and these antennas actually by singlet energy transfer. So singlet energy transfer is dumped off here into the betaine in 33 picoseconds. And then this just returns to the ground state, generating heat. So in this case, this is much faster than the electron transfer. So the electron transfer quantum yield is only about 1%. So essentially everything is dumped with heat. What that means, of course, is when you have a solution of this material, then you have, and you illuminate it with white light, then you have some of these molecules in the colorless dihydroindolazine form, some with the control unit in the colored form, the quenching form, and the ratio of those two is determined by the light intensity and the temperature. And the brighter the light, the more you'll have in this form down here. The dimmer the light, the more you'll have in the non-quenching form up here. So that's the idea behind the photoregulation. Does it work? Well, yeah, here's 13 experiments. These hollow circles here are white light intensity, going up and then coming back down again. And then up here, the solid circles are the quantum yield of photoinduced electron transfer, quantum yield of charge separation of the solution. And we start out here at about 82% when the light's dim. And then as the light gets brighter, then you see the quantum yield goes down because of this quenching effect. In this case, it goes down to, I don't know, about 32 or so. We've got as low as about 27. It all depends on how much white light you use. And then when we bring the white light back down again, then the quantum yield goes back up. So we have this inverse behavior of quantum yield relative to light intensity, similar to what you see in the non-photochemical quenching. And here I show that in a little bit different way. I multiplied the quantum yield of charge separation times the light intensity to get a measure of the overall yield of charge separation shown here. You can see when the light intensity is low, then the yield of charge separation is linear with light intensity, as you'd expect for any kind of a system. But when the light intensity gets high, then it levels off due to this control behavior. And here you see that same graph on the left. On the right is a graph of non-photochemical quenching in orange trees. Couldn't find cyanobacteria, but I did find orange trees working by a little bit different mechanism. But you see the same effect down here. The photosynthetic electron transport linear with photon flux, and you get up to high photon flux, and it levels off due to the M to Q. So we have here then a first stab, let's say, at learning how to regulate photosynthesis. And you can also incorporate in these systems carotenoid photoprotection and things of that sort. Okay, so I've gotten pretty much my allotted time here. I'd like to have a few conclusions. First of all, doing large-scale water oxidation to produce fuels using sunlight is certainly practical, and the way we know that is that photosynthesis does it. So if anybody tells you it'll never work, well, it does work. That's where we get our energy right now. Secondly, we can make artificial photosynthetic systems that do use light to split water and make hydrogen. They don't work very well, but they can be done, and we're making them better. We have to solve a lot of problems before this is practical. But we have to solve those problems, I think, if we're going to continue with human society in the way we've gotten used to it. We have to ultimately find alternatives to fossil fuels. And I think some sort of solar energy conversion is going to be not the only way to go. So I'll conclude with, again, going back to Giacomo Chamichan in that same article in Science Magazine. And you see he has this vision there of getting rid of fossil fuels using artificial photosynthesis. And thinks that wouldn't be a bad thing, and I have to agree with that. I'd like to thank my collaborators, Tom and Anna Moore. I've been working with them for 30-some-odd years in this general area. John Lindsay, mentioned some work with him. Tom Maloof, mentioned work with him. The other principal investigators in our EFRC, we have 11 of them working at Arizona State. A lot of postdocs and students. I listed the references on those slides as I went through. And finally, the Department of Energy for funding this research. And thank you all for your attention.
Hi. I had a question about the linkages between the electron acceptors in your artificial photosynthetic group. Do the linker attachments between those groups play an important role in charge separation? And how important is that based on?
Sure. The linker, if you look at the simple Marcus theory, then you find that the donor acceptor separation controls in the first approximation the electronic coupling, between the initial and final states, and that's what determines, one of the things that determines the rate. So the further apart the systems are, the slower the rate. And of course, if there's linker in between, then you can have contributions from what's called superexchange. But it's the same, basically the same kind of exponential fall off of rate with separation. And so we use that to control the rate. And in some of the systems I showed you at the beginning, it was very fast, like a picosecond or so. So that's, of course, highly efficient. In the regulatory system, you notice it was a lot slower. And the reason was there we had to have the electron transfer significantly slower than the quenching of the chlorophyll excited state by the regulatory part, or it wouldn't work. So we had to slow down electron transfer so that the quenching by the betaine form of that photochrome could be faster. So yeah, we control the rates by those linkages, and it's a trade-off between having a real fast rate and more rapid charge recombination of the initial state, and a slower rate with slower recombination, but also lower yield if you get too slow. So you have to tune that linkage to get what you want. Excuse me, maybe you can use the microphone there.
You had the reaction centers where you could split the charge to positive and negative. I wonder what would happen if you stack them in series. Would this increase the current? Or?
Well, it would increase the voltage, in principle, and that's The question is if we stack the artificial reaction centers in series in some way, would that be beneficial? And the answer to that basically is what we're doing in that tandem cell I showed at the end. Those are being stacked, but they're simply by virtue of having a wire between essentially one end of one and the other end of the other. So in a sense, that's what we're doing when we're making that tandem system. But yeah, if you could stack them chemically in some way, people have certainly thought about trying to do that, and you do that with semiconductors, and you get an increase in voltage. Of course, you also, if you do that, if you have the two species absorbing a different wavelength, you have to make sure that you match the photon flux to the different absorptions, because the overall current is going to be limited by whatever of those stacked species is the one that absorbs photons least often or least effectively. So you have to design those systems correctly if you want to have good yield. Yeah, so the question was, can you, in a system like that, photoprotective system at the end, can you use basically the part of the solar spectrum that you select out to control the functioning of the photoprotection? And there you certainly can, because of the fact that that photoprotective unit absorbs light in a certain range. And there are a lot of these photochromes, and they can be tuned to absorb in different wavelength regions. So it would be possible to do that. In the ideal system, I think you would have such system that was so robust that you wouldn't ever need any photoprotection. But from my point of view, achieving that with any sort of organic species is going to be pretty hard. Because photons are very energetic, and oxygen, which you're producing, is a good oxidizing agent.
So going back to the fullerenes that you used, instead of using, say, the buckyball that you had demonstrated up there, have you ever thought of using a carbon nanotube to further direct the electron you're capturing there?
Some people Dirk Gouldy, for example, has done some work with injecting into carbon nanotubes and trying to make devices of various sorts. And they've had some success. I don't know of any of the efficiencies that are super high, but you have to be careful with the carbon nanotubes that you don't absorb all the light with the nanotube instead of your dye, or you don't quench your dye by energy transfer or something like that instead of by electron transfer. But in principle, you could do that sort of thing. We haven't. Some people have been looking at things. The nice thing about the C60s and probably the nanotubes as well, and porphyrins and carotenoids and all these things, is that they have low reorganization energies for electron transfer because they're large delocalized pi systems where the electron density or the hole density gets spread over a big area. And that has the consequences in Marcus theory of two things. One is it allows charge separation to be fast and charge recombination to be slow. And the other thing it does is if you have these localized systems, they're not as sensitive to the effects of solvent on the energy of the charge separated species. So they will work even at very low temperatures. For example, that 3-part system I showed you there works down at 4 degrees Kelvin, does electron transfer down there. And so does photosynthesis, but I don't know of any other artificial systems that work at that temperature. Most of them will stop when you get down even to a frozen liquid. The reason is that you're pushing the energy of the charge separated state up too high, so the driving force is not large enough for electron transfer. Because solvation plays such a big role in stabilizing the ions that you're making.